The purpose of this presentation is to consider a type of problem that calculus teachers and calculus textbooks refer to as related rates problems. In this presentation, we're going to be taking a look at the basic plan. We will work an example, but only for the purpose of highlighting the various steps in solving such problems. You always can tell that you're dealing with a related rates problem because the problem mentions two or more changing quantities. Oftentimes, those quantities are changing with respect to time, as they are in our example problem. What are the steps when we're working with a related rates problem? Well, the first step is to get a labeled diagram. Sometimes a diagram is provided for us and we just have to label it, and sometimes we have to make our own diagram. The second thing to do is to identify the known and wanted rates. We'll express these using calculus notation. The third thing to do is to get an equation to relate the variables. After we've got that equation that relates the variables, we'll differentiate with respect to time. Now, this step will involve implicit differentiation. The last thing we want to do is solve for any unknowns, and in particular for the wanted rate or wanted rates. Look at that first step, getting a labeled diagram. Here's a problem that we can use for example purposes. The legs of a right triangle are changing length. One leg is growing at a rate of 2 inches per second. The other is shrinking at a rate of 1 inch per second. At what rate is the hypotenuse changing when the growing leg is 12 inches and the shrinking leg is 16 inches? And by the way, is that hypotenuse shrinking or growing? So, as we approach this problem, we draw for ourselves a nice right triangle. Now, unlike what you might expect, we're not going to put these measures of 12 inches and 16 inches on the diagram. It's true that at one moment in time, the diagram does have those lengths. However, those legs are shrinking and growing, so we don't want to get the idea that they're always 12 and 16 because they're not. So instead what we'll do is we'll make up variable names for them. The names aren't important. Here I'm choosing A and B for the legs, and I'll call the length of the hypotenuse C. Then I'll note which is the growing leg and which is the shrinking leg. Again, not putting those lengths of 12 and 16 inches on the diagram quite yet. Now that we've got our diagram in place, it's time to identify the known and wanted rates. So in part of the statement of the problem, it says that one of the legs is shrinking at a rate of 1 inch per second. So because it's shrinking, it's getting smaller, its rate of change is negative. So one of the known rates is what I'm calling dA dt, to reflect that the leg labeled A is shrinking at a rate of 1 inch per second. The other leg is growing, so it has a positive rate of change. So dB dt is equal to 2. The question asks, at what rate is the hypotenuse changing? So there's the wanted rate right there. The next step is to get an equation to relate the variables. One of the things you'll find when you're working these problems is that you need a fair amount of room to take care of all the work that goes on in all the many steps. So I'm going to just move this diagram over for a second. And when we talk about relating the variables, the specific variables are those that are mentioned in the known and unknown rates. In this case, we need an equation that relates A and B and C. Fortunately for us, this is a right triangle, and there's a very familiar relationship between the side lengths of a right triangle. The side lengths of a right triangle are, of course, related by the Pythagorean equation a squared plus b squared equals c squared. Now that we've got that equation ready, we're going to begin to differentiate with respect to time. What that means is we're going to find the derivative of each of these terms, but we're going to do so with respect to time. So whereas the derivative of a squared with respect to a is 2a, we also need to multiply by the derivative of that inside function a with respect to time. Similarly, we'll have 2b times the derivative of b with respect to time, and likewise 2c times the derivative of c with respect to time. At this stage of the game, we're ready to solve for any unknowns. We already know the quantity dA dt, so we can replace that with a -1. Likewise, we know dB dt, so we can replace that with a 2. Now what about these lengths a and b? A, you'll remember, represents the size of the shrinking leg at this moment in time, and that's 16. So we can replace the a with a 16. Similarly, we can replace b with 12. And now I realize that I've got an equation with two variables in it. One of the variables is c, the other one is dc dt. I'm not very good at solving equations with two variables in them, so what I'd like to do is to simplify things a bit. The first thing I notice is that I've got factors of 2 all over the place, and if it's okay with you, I'd like to cancel those right now. Well, that simplified things a bit. What about c? At the moment in time, when the growing leg is 12 and the shrinking leg is 16, I can know the length of the hypotenuse. So I'll take out the c and I'll replace it with what it's equal to. I find that out by using the equation that relates the variables. It turns out that the length is 20 in this case. That allows me to solve for dc dt and finally answer the question, since this derivative is positive, we can say that the hypotenuse is growing. A nice follow-up to the problem that we just worked might be this problem. So I've changed the rates a little bit, and I've also changed the lengths too. You might pause the video at this point and ask yourself if you have what it takes to solve this problem. The answer will appear in a few moments. Hey, thanks for watching.